Welcome to the Insightful Professor. In this video, we'll continue our discussion of intrusion detection. We'll examine the features and characteristics that are considered essential to an intrusion detection system, and we'll discuss how these systems work. We'll actually take a quick look at an actual system called Snort. An intrusion detection system consists of three logical components. The first of these components would be the sensors. Sensors are responsible for collecting data and forwarding this information to the analyzer. Input for a sensor may be any part of a system that could contain evidence of an intrusion, such as network packets, log files, and system call traces. The second component would be the analyzers. Analyzers receive input from one or more sensors or from other analyzers. Analyzers are responsible for determining if an intrusion has occurred. The output of an analyzer is an indication that an intrusion has occurred and possibly evidence supporting this conclusion. An analyzer might provide guidance about actions to take as a result of the intrusion. Sensor inputs may also be stored for future analysis and review in a storage or database component. And finally, the third component is the user interface. The user interface enables a user to view output from the system or control the behavior of the system. In some systems, the user interface may equate to a manager, director, or console component. We often classify an intrusion detection system based on the source and type of data analyzed. A host-based IDS, or HIDS, monitors characteristics of a single host and events occurring within that host for evidence of suspicious activity. A network-based IDS, or NIDS, monitors network traffic for particular network segments or devices and analyzes network, transport, and application protocols to identify suspicious activity. A distributed or hybrid IDS combines information from a number of sensors, often both host and network-based, in a central analyzer that is able to better identify and respond to intrusion activity. So an IDS may use a single sensor and analyzer, such as HIDS on a host or NIDS on a firewall. A host-based intrusion detection system adds a specialized layer of security software to vulnerable or sensitive systems, such as database servers and administrative systems. The HIDS monitors activity on the system in a variety of ways to detect suspicious behavior. In some cases, an IDS can halt an attack before any damage is done, but its main purpose is to detect intrusions, log suspicious events, and send alerts. The primary benefit of an HIDS is that it can detect both external and internal intrusions, something that is not possible either with network-based IDSs or firewalls. A network-based IDS monitors traffic at selected points on a network or interconnected set of networks. The NIDS examines the traffic packet by packet in real time or close to real time to attempt to detect intrusion patterns. The NIDS may examine network, transport, and/or application-level protocol activity. Note the contrast with a host-based IDS. A network-based IDS examines packet traffic directed toward potentially vulnerable computer systems on a network. A host-based system examines user and software activity on a host. A typical network-based IDS facility includes a number of sensors to monitor packet traffic, one or more servers for NIDS management functions, and one or more management consoles for the human interface. The analysis of traffic patterns to detect intrusions may be done at the sensor, at the management server, or some combination of the two. Sensors can be deployed in one of two modes, inline and passive. An inline sensor is inserted into a network segment so that the traffic that it is monitoring must pass through the sensor. One way to achieve an inline sensor is to combine NIDS sensor logic with another network device, such as a firewall or a LAN switch. This approach has the advantage that no additional separate hardware devices are needed. All that is required is NIDS sensor software. An alternative is a standalone inline NIDS sensor. The primary motivation for the use of inline sensors is to enable them to block an attack when one is detected. In this case, the device is performing both intrusion detection and intrusion prevention functions. More commonly, passive sensors are used. A passive sensor monitors a copy of network traffic. The actual traffic does not pass through the device. From the point of view of traffic flow, the passive sensor is more efficient than the inline sensor because it does not add an extra handling step that contributes to packet delay. This figure illustrates a typical passive sensor configuration. The sensor connects to the network transmission medium, such as a fiber optic cable, by a direct physical tap. The tap provides the sensor with a copy of all network traffic being carried by the medium. The network interface card for this tap usually does not have an IP address configured for it. All traffic into this NIC is simply collected with no protocol interaction with the network. The sensor has a second NIC that connects to the network with an IP address and enables the sensor to communicate with an NIDS management server. Consider an organization with multiple sites, each of which has one or more LANs with all of the networks interconnected via the internet or some other wide area network. For a comprehensive NIDS strategy, one or more sensors are needed at each site. Within a single site, a key decision for the security administrator is the placement of the sensors. This figure illustrates several possibilities. In general terms, this configuration is typical of larger organizations. All internet traffic passes through an external firewall that protects the entire facility. The traffic from the outside world, such as customers and vendors that need access to public services, such as web and mail, is monitored. The external firewall also provides a degree of protection for those parts of the network that should only be accessible by users from other corporate sites. Internal firewalls may also be used to provide more specific protection to certain parts of the network. A common location for an NIDS sensor is just inside the external firewall, location 1 in this figure. This position has several advantages. It sees attacks originating from the outside world that penetrate the network's perimeter defenses, the external firewall. It highlights problems with the network firewall policy or performance. It sees attacks that might target the web server or FTP server. Even if the incoming attack is not recognized, the IDS can sometimes recognize the outgoing traffic that results from the compromised system. When a sensor detects a potential violation, it sends an alert and logs information related to this event. The NIDS analysis module can use this information to refine intrusion detection parameters and algorithms. The security administrator can use this information to design prevention techniques. Typical information logged by an NIDS sensor includes the following: the timestamp, usually a date and time; connection or session ID, typically a consecutive or unique number assigned to each TCP connection or to like groups of packets for connectionless protocols; event or alert type; rating, such as priority, severity, impact, confidence; network, transport, and application layer protocols; source and destination IP addresses; source and destination TCP or UDP ports or ICMP types and codes; number of bytes transmitted over the connection; decoded payload data, such as application requests and responses; state-related information, such as authenticated username. Intrusion detection is motivated by a number of considerations, including avoiding damage or harm, or at least minimizing it. The goal here is to quickly detect the intrusion. The intruder can be identified and ejected from the system before any damage is done or any data has been compromised. Thus, the sooner the intrusion is detected, the less the amount of damage and the more quickly that recovery can be achieved. The presence of an IDS serves as a deterrent, acting to prevent intrusions. Additionally, we wish to learn from experience. Intrusion detection enables the collection of information about intrusions. This can be used to strengthen intrusion prevention measures. Thus, intrusion detection is based on the assumption that behavior of the intruder differs from that of a legitimate user in ways that can be quantified. Unfortunately, we cannot expect there will be an exact distinction between an attack by an intruder and normal use of resources by an authorized user. Thus, we must realize that there will be some overlap. This makes the process of intrusion detection a challenging undertaking. A loose interpretation of intruder behavior, which will catch more intruders, will also lead to a number of false positives or false alarms, where authorized users are identified as intruders. An attempt to limit false positives by a tight interpretation of intruder behavior will lead to an increase in false negatives, or intruders not identified as intruders. We now consider desirable features or characteristics of an IDS. The system must run continually with minimal human supervision. It must be fault tolerant in the sense that it must be able to recover from system crashes and reinitializations. It must resist subversion. The IDS must be able to monitor itself and detect if it has been modified by an attacker. It must impose a minimal overhead on the system when it is running. It must be able to be configured according to the security policies of the system that is being monitored. It must be able to adapt to changes in system and user behavior over time. It must be able to scale to monitor a large number of hosts. It must be able to provide graceful degradation of service in the sense that if some components of the IDS stop working for any reason, the rest of them should be affected as little as possible. And finally, it must allow dynamic reconfiguration. This means we need the ability to reconfigure the IDS without having to restart it. We've described functional characteristics or qualities of an IDS. But how does it actually work? How does it detect intrusions? There are two basic categories of intrusion detection techniques: anomaly detection and misuse detection. Misuse detection is also called signature or heuristic detection. With anomaly detection, the system uses models of intended behavior of the users and applications. It detects deviations from this normal behavior, interpreting them as a problem. It assumes an attack differs from this normal behavior. The advantage of this approach is that it can detect previously unknown attacks, something novel. The disadvantage of this approach is that it is difficult to train in highly dynamic environments. Consider a situation where some user typically logs in around 10 a.m. That user reads their mail, then performs database transactions, generally takes a break between noon and 1 p.m., and encounters very few file access errors. Typical normal behavior. During its operation, the system notices that this user logs in at 3 a.m., starts using compilers and debugging tools, has numerous file access errors. Because of the deviation from what we've deemed to be normal, this activity will be flagged as suspicious. Note once again that this is a manifestation or evidence of an intrusion or suspected intrusion. This approach to intrusion detection can only identify known attacks, that is, those whose signatures have been recorded for use by the IDS. Thus, misuse detection defines what is wrong, using these attack descriptions or signatures and matching them against an audit data stream, looking for evidence of these known attacks. The advantage to this approach is that it focuses the analysis on audit data and typically produces few false positives. The disadvantage, however, is that it can detect only attacks for which it has a signature. That is, if a novel attack is introduced, the system has no knowledge of what this thing looks like, and it can't respond. Consider as an example, someone creates a symbolic link to a Unix system's password file, and then executes a privileged application that accesses this symbolic link. This attack exploits the lack of file access checks. The anomaly detection approach involves first developing a model of legitimate user behavior by collecting and processing sensor data from the normal operation of the monitored system in some type of training phase. This may occur at distinct times, or there may be a continuous process of monitoring and evolving the model over time. Once this model exists, current observed behavior is compared with the model in order to classify it as legitimate or anomalous activity in a detection phase. There are two key issues that affect the relative performance of these alternatives: efficiency and cost of the detection phase. The monitored data is first parameterized into desired standard metrics that will then be analyzed. This step ensures data gathered from a variety of possible sources is provided in standard form for analysis. There are a variety of classification approaches used in anomaly detection. There's a statistical approach where the observed behavior is analyzed using invariant, multivariate, and time series models of observed metrics. There is a knowledge-based approach, which uses an expert system that classifies observed behavior according to a set of rules that model legitimate behavior. With machine learning, the system automatically determines a suitable classification model from the training data using data mining techniques. Signature or heuristic techniques detect intrusion by observing events in the system and applying a set of signature patterns to the data or a set of rules that characterize the data, leading to a decision regarding whether observed data indicates normal or anomalous behavior. Signature approaches match a large collection of known patterns of malicious data against data stored on a system or in transit over a network. Signatures need to be large enough to minimize false alarm rate while still detecting a sufficiently large fraction of malicious data. This is widely used in antivirus products, network traffic scanning proxies, and in NIDS. The advantages are relatively low cost in time and resource use, and its wide acceptance. The disadvantages relate to significant effort required to constantly identify and review new malware to create signatures able to identify it, and the inability to detect zero-day attacks for which no signatures exist. Rule-based heuristic identification involves use of rules for identifying known penetrations or penetrations that would exploit known weaknesses. Rules can be defined that identify suspicious behavior even when the behavior is within the bounds of established patterns of usage. Rules used in these systems are specific to the machine and operating system. The most fruitful approach to developing such rules is to analyze attack tools and scripts collected on the internet. These rules can be supplemented with rules generated by knowledgeable security personnel. In this latter case, normal procedure is to interview system administrators and security analysts to collect a suite of known penetration scenarios and key events that threaten the security of the target system. As with host-based intrusion detection, network-based intrusion detection makes use of signature detection and anomaly detection. Unlike the case with HIDS, a number of commercial anomaly NIDS products are available. One of the best known is the Statistical Packet Anomaly Detection Engine, or SPADE. There are many types of attack that are suitable for signature detection, as we note here. We'll begin with application layer reconnaissance, and note that most NIDS technologies analyze several dozen application protocols. What the NIDS is looking for is attack patterns that have been identified as targeting these protocols. Examples of attack include buffer overflows, password guessing, and malware transmission. Also suitable would be transport layer reconnaissance. Here, the NIDS analyzes TCP and UDP traffic and perhaps other transport layer protocols. Examples of attacks are unusual packet fragmentation, scans for vulnerable ports, and TCP-specific attacks, such as SYN floods. With network layer reconnaissance, an NIDS typically analyzes IPv4, IPv6, ICMP, and IGMP at this level. Examples of attacks are spoofed IP addresses and illegal IP header values. For unexpected application services, the NIDS attempts to determine if the activity on a transport connection is consistent with the expected application protocol. An example would be a host running an unauthorized application service. Attacks suitable for anomaly detection include denial of service attacks. We've already discussed these in an earlier video. A scanning attack occurs when an attacker probes a target network or system by sending different kinds of packets. Using the responses received from the target, the attacker can learn many of the system's characteristics and vulnerabilities. Thus, a scanning attack acts as a target identification tool for an attacker. Scanning can be detected by atypical flow patterns at the application layer, transport layer, and network layer. We'll also note here that many worms perform scanning. And now we'll take a brief look at an available network intrusion detection system called Snort. Snort is an open source, highly configurable, and portable host-based or network-based IDS. Snort is referred to as a lightweight IDS and has the following characteristics. It's easily deployed on most nodes. It exhibits efficient operation that uses a small amount of memory and processor time. And it's easily configured by system administrators who need to implement a specific security solution in a short amount of time. Snort can perform real-time packet capture, protocol analysis, and content searching and matching. It can detect a variety of attacks and probes based on a set of rules configured by a system administrator. A Snort implementation can be configured as a passive sensor, which monitors traffic but is not in the main transmission path of the traffic, or as an inline sensor, through which all packet traffic must pass. In the latter case, Snort can perform intrusion prevention as well as intrusion detection. A Snort installation consists of 4 logical components, as indicated in our figure here. The packet decoder processes each captured packet to identify and isolate protocol headers at the data link, network, transport, and application layers. The decoder is designed to be as efficient as possible, and its primary work consists of setting pointers so that the various protocol headers can be easily extracted. The detection engine does the actual work of the intrusion detection. This module analyzes each packet based on a set of rules defined for this configuration of Snort by the security administrator. In essence, each packet is checked against all the rules to determine if the packet matches the characteristics defined by a rule. The first rule that matches the decoded packet triggers the action specified by the rule. If no rule matches the packet, the detection engine discards the packet. For each packet that matches a rule, the rule specifies what logging and alert options are to be taken. When a logger option is selected, the logger stores the detected packet in human-readable format or in a more compact binary format in a designated log file. The security administrator can then use the log file for later analysis. For each detected packet, an alert can be sent. The alert option in the matching rule determines what information is included in the event notification. The event notification can be sent to a file, to a Unix socket, or to a database. Alerting may be turned off during testing or penetration studies. Using the Unix socket, the alert can be sent to a management machine elsewhere on the network. Snort uses a simple, flexible rule definition language that generates the rules used by the detection engine. Although the rules are simple and straightforward to write, they are powerful enough to detect a wide variety of hostile and suspicious traffic. Each rule consists of a fixed header and 0 or more options. The header has the following elements: an action, which tells Snort what to do when it finds a packet that matches the rule criteria. The protocol. Snort proceeds in analysis if packet protocol matches this field. Snort recognizes 4 protocols: TCP, UDP, ICMP, and IP. The source IP address designates the source of the packet. The rule may specify a specific IP address, any IP address, a list of specific IP addresses, or the negation of a specific IP address or list. The negation indicates that any IP address other than those listed is a match. The source port designates the specified protocol, for example, a TCP port. Port numbers may be specified in a number of ways, including specific port numbers, any ports, static port definitions, ranges, and by negation. Direction takes one of 2 values: unidirectional or bidirectional. Bidirectional tells Snort to consider the address port pairs in the rule as source followed by destination or destination followed by source. The bidirectional option enables Snort to monitor both sides of a conversation. The destination IP address and destination port respectively designate the destination IP address of the packet and its destination port. The rule header may be followed by 1 or more options. Each option consists of an option keyword, which defines the option, followed by arguments which specify details of the option. Here we present a list of possible actions and brief descriptions of these actions. Notice that the last 3 actions in the list, drop, reject, and sdrop, are only available for inline mode. Snort has 4 major categories of rule options. These are metadata, which provides information about the rule, but does not have any effect during detection. Payload, which looks for data inside the packet payload, and these can be interrelated. Non-payload looks for non-payload data. And post-detection. These are rule-specific triggers that happen after a rule has matched a packet. This figure provides an example of some of the rule option categories that we just described. If you're interested in further examining Snort, visit www.snort.org. There you can find documentation and additional information about the product, and you can also download a copy of the software. So what have we covered in these videos? We've discussed intruders and intruder behavior We talked about the basic principles and requirements of intrusion detection. We talked about two approaches to performing analysis: anomaly detection and misuse detection, also called signature or heuristic. We talked about host-based intrusion detection and compared and contrasted that with network-based intrusion detection. And we provided a little insight to an example IDS in the form of Snort.